to finish up a brief bit on the audio, which is the 3-note thing, right? What we were talking about last time is how it's basically storing and processing this song is by, we have well, let me just load the code. Let me just pull it up and add them here. Right, so we had all of this stuff here, and what was going on? Oh, that's probably a little unreadable, isn't it? Let me change the theme. I wish they had an easy button for this. Okay, all right, so solarize it. So, all right, so what was going on, right? We have all those data statements down at the bottom, and the first 12 of them here were to set the base frequencies for each, the sort of main frequency for the highest note in the highest octave worth of notes. Okay, and then all the other octaves note frequency values were computed by dividing these numbers by however many powers of 2 were necessary, right? Because whenever you go up an octave, you double your frequency, and so whenever you go down an octave, you have your frequency. Okay, and it makes sense then that 34 through whatever and the 64 whatever at the end, right, is that this one is not quite double of that one, and that makes sense because it should be just shy of 1 octave up. Okay, it should be 11 half steps up instead of 12. Okay, so there's that, and then the data statements here are for each of the 3 voices, and it's oriented voice 1, voice 2, voice 3. Okay, now for you guys, when you start encoding the song, right, if you want to play your part, just plop it in for one of the 3 voices. It doesn't really matter, and just put a 0 in for the other 2. Okay, because, and then it'll just play your tone only. Okay, now it'll be a little slow and it's a little janky, but it'll work. Okay, and because what am I going to do ultimately when we put all this together is take all of each of your stuff and basically have just this giant data section in order. Okay, now the other thing I'll have to do is maybe expand the array or use the better way to do this, which is to use external files and use the disk instead of trying to keep everything in memory. Okay, but we'll deal for just making sure that you've got the right notes in and that it sounds correct. Just use this program from the thing, and remember there was that one typo on whatever line it was. Yeah. Where there was a missing equals. So other than that, right, it's ready to go. Just replace your data statements. Okay, so what was up with the long pause? You know, why the long face? Because it was loading everything into these giant arrays, right? So it made 3 arrays, each of which were 3 by 201. And it's storing in them for each note, or for each voice rather. So each note is a row, and each column of the 3 is one of the voices. It's going to have the high frequency byte, the low frequency byte, and the control byte for each of the 16 different, or for every 16th note. Okay. Now in our case, it allocates 201 of these things, which is just over 12 and a half measures worth from the song. And oh, by the way, I found out what the song is.
What is it?
It is "Now Thank We All Our God." It is a Lutheran hymn, basically. So yeah, Well, you're from Minnesota. Like, isn't everybody up there a Lutheran? Yeah. Yeah. Oh, just imagine growing up in the Bible Belt, bro. Um, yeah. So, um, yeah. Ah, well, right. So I took a recording of it playing and posted it to Facebook and said, "Hey, friends, Facebook Hive Mind, anybody recognize this?" And one of my very musical and choral, friends was like, "Oh yeah, it sounds like blah." And then I separately sent it to Diane Norton in the library and Sarah Williams in the music department. And Diane replied back with the same hymn, not having known about the Facebook Hive Mind thing. So, and then I found it on YouTube, the song, and played it, and it was like, okay, yeah, they clearly took some artistic liberties here because the Commodore can only play three notes at a time, and the hymn obviously was um, uh, meant for organ and chorus, so there's a lot more voices there. And there's a couple different versions of it I found, like different arrangements and different organists kind of being like, making, improvising in some sense. Yes, so sorry, none of you get the $5. Hmm. Yes. Yep. Yes. Let me think for a second. Yes. So if you change that 80 to something else, it goes faster or slower. Yeah. Right. So, yeah, because what I think you'd want to kind of deal with this and this is why I was mentioning the sort of measure by measure idea, which is if we encoded each measure where there was a number at the front of each measure's worth of stuff that says what was the smallest time interval that occurred in that measure, then you could kind of condense things a little bit. I'm not sure if it's worth it. And for the sake of right now, let's just not worry about that and just encode it as just every 16th note. Okay. Which well, okay. So the let me be clear. The data lines are not encoded every 16th node. The array is. Right. 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 Well, I mean, yeah, but like, okay, a better way in basic, right? Yeah, to some extent, right? But ultimately, okay, when we say better way, um, basic is slow, right? So you know what the better way is? Machine language. Yeah, because it's shitloads faster. Okay. Um, and we can do basically everything here, but obviously we'll speed up the execution time by probably a factor of 10, but our development time will go up by a factor of 100. Uh, well, okay. You could, what, you mean an assembler? Well, we don't need to write one. There's already is one. Hmm. Yes. Okay. Fair enough. So that actually does bring up 2 points. Okay. One is the basic as it is slow because it's being interpreted on the fly. Okay. There were and are programs called basic compilers that take BASIC and spit out machine code. Those would obviously run a lot faster because the interpretation has happened in advance. Okay, so there were BASIC compilers that you could get back in the 80s. So there's that. Now, if you wanted to write machine language stuff, starting with a high-level language, if that high-level language is BASIC, then you would need one of these BASIC compilers. If it's C, well, wouldn't it be great if there was a C compiler that could compile down to 6502 machine language? And there is. It's called CC65.
Wow.
Okay. So, yes, there is a pretty robust C compiler that will spit out 6502 machine code. And in fact, it has one of the flags that you give it is to say that you're programming for a C64. And so it knows all the C64 specific idiosyncrasies. Which is and any other 6502 based system, it knows the idiosyncrasy, right? Because the Apple II and the Commodore and the PET and the right, a lot of different 6502 systems have slight variations, and it knows all of those. Okay, okay, but unfortunately, you guys are hosed because right now you have to program in BASIC, which I'm doing deliberately, even though it is kind of hamstringing you. All right, so the big pause is basically because it's pre-computing this giant array of stuff, okay? And it's pre-computing it every time we run the program. That's stupid, right? What would make much more sense is to split this program into really two chunks. The part that pre-renders everything down to these arrays, store those on disk, and then the player that reads that from disk and actually outputs it. Because then we only have to render the song once, and we can hit run to play it, and it'll just play. There's no pre-computing left to be done. Okay. Guess what one of your assignments is? To do that. Yes, exactly. Because I'm a horrible person. Okay. Okay. So, but in terms of the old Wabash stuff, all you've got to do for your chunk is just like I said, replace, the data, one of the data sections with your stuff, and just put a 0 for the other two voices so that they're silent. Okay. And then just run it and see what it sounds like, and it hopefully will sound roughly like your part of old Wabash. On the subject of old Wabash, I forgot about something. Because what's your greatest joy? What's our greatest joy? Yeah, what's our greatest joy?
What?
No, to shout the chorus. Come on, guys. Ah, the
Like
chorus.
the little like cat meme with like the loading symbol.
Hmm.
Yeah.
Okay. All right. So the chorus. I forgot about one minor detail, if you'll pardon the pun there.
Oh, you need a key change.
Oh, yes. Because the chorus, not only does it change key signature, it also changes time signature. I forgot about this.
Wow.
Yeah. So the the key signature changes, okay, and it changes so that uh, anytime, well, okay, you see a note that corresponds to these, which I think what was B, um, no, G. Um, no, yeah, B is what I said. Okay, I was looking at the wrong one. Um, is are flats unless otherwise indicated. Okay, and the way that it becomes unflat is if you see this symbol there, which is the symbol for natural. Okay, so B's in that section of the song, which conveniently is only on page 3. Okay, which means none of you have to deal with a key or time signature change in the middle of your stuff. Okay, you only have one key signature and one time signature. Okay, so that's nice. So all B's are flat in the chorus, unless indicated with where the mouse cursor is the natural symbol. Okay. Now, the other thing is the time signature changes to you see underneath the word chorus, it's got sort of the C with a bar through it. That's the symbol for common time, which is 4/4. Okay. So what it means is those measures have how many 16th notes total? They have 16 worth of them. So 4 quarter notes. Okay. And I think I said there were no whole notes in the song, but of course I'm wrong because what is dear there? Right. Dear in the vocals is an entire whole note. So it's the entire 16 16th notes. Okay. Make sense? Yeah? Okay.
So, okay.
Hmm?
Not necessarily the difficulty in getting the notes to play. It is the timing is is there what page like is there a formula in terms of like how to know the timing because this is going to be a lot of trial and error otherwise.
No, it's not.
This is not like is
You
there
just
like
literally go note by note, right?
I don't know. I'm saying like when you change like did you change tempo at any point
Oh,
or like if you have
okay.
because you can't just use an overall like you have to encode that somehow because we can't just have one singular tempo where it plays it at it because it won't make sense. So like
Yes, actually, it will because um, because there's no indication in the song that the tempo changes, only the time signature changes. Okay, and now there can be an indication of a tempo change. There isn't in this song.
there isn't okay
Okay, so the tempo change we would have to, that loop that goes 1 to 80.
that's a change.
We would have to change that. Now, fortunately, we don't have to because, like I said, the tempo doesn't change here. Okay. I mean, unless you're doing the chapel sing version, right?
Yeah.
In which case it's,
Wait a minute.
yeah. Okay. So, in terms of y'all encoding it, basically the only difference for those of you who've got the third page is that there's going to be 16 16th notes worth of stuff in every measure instead of only 12, right?
I mean, it doesn't really
But it doesn't change
matter
anything.
because like the measures are irrespective of the array.
Yeah, the array doesn't know what measures are. Only you do. Okay. Um, yeah,
So would a note the 16th time be the same duration?
exactly. It's still 4/16 notes. It's just that each measure in this section is longer. There's more notes within it. Okay. But in terms of the values of the durations of each note, they're all the same. Okay. Number of 16th notes. So the only difference is that, of course, the chorus has whole notes, which are 16 16ths, whereas the rest of the song only could have up to a dotted half note, which would have been 12 16ths.
I mean, in all seriousness, it doesn't actually really change the time signature because you can treat 6/8 like 2/2, and then this is just 4/4, so it doesn't matter.
Right.
It just happens to
Because you could always just subdivide the measures, right? So yeah, so the time signature change only will affect making sure that you're not missing notes by making sure you're counting correctly. The key signature is a minor difference, right? It's just that if you're not doing page three, B's are by default natural, and if you are doing page three, B's by default are flat. Okay, and that's it. Yeah. Okay. So, um, anyway, so that minor detail, and I will stop making minor puns. Yeah, so just replace one of the voices with your notes and delete the others, but make sure you leave a zero, data of zero at the end because that's how the loop thing that makes the array knows to not do it. Yeah,
are all these the same length?
no,
No, some of them like so just fill the rest with zeros.
yeah,
Fill them they're by default.
yeah, they're all zeros to start with, and then it just yeah. Okay, so yeah, so that's why you don't have to worry about it, and you don't have to write any special code to make sure your music works. Just plug in your numbers, listen to them, and they should hopefully be good. Yeah.
What was the equation for numbers again?
Oh, well, it's in the book, but let me go back to the PowerPoint. It was this, right? So duration times 8 plus octave times 16 plus note, where the um, which, what did we say the starting note was? It was something stupid like A sharp. Yeah, I don't remember. I think, oh no, it's because what I did was I decoded, get it out of here. Um, I decoded the very first note from the song that was given. So the 594, if we go back to, well, so the very first note in the song was, I think, a 594, which corresponded to duration 4, octave 5, note 2. And then the frequency I got, I looked it up and it was C5. And if that's note 2, then B is note 1, which means A sharp is note 1 or note 0. Okay, just to, yes, 2/16 notes.
So
Okay.
all of this is assuming with the baked, so this is the baked-in assumption with that specific mapping, that it is 16th notes are the smallest duration. If not, it would have had to been 32 times right there.
Yeah, we'd have to change the formulas
So
here.
it'd be different, but
Yeah,
it would be a power of 2 up because it's 30
right.
seconds.
Yeah, as the next power of 2, right? Yeah, so fortunately we don't have to worry about that because the smallest duration is 16th notes. If we had a song with 32nd notes, we'd be hosed. We'd have to redo this.
It just be 16 to 32.
Well, yes, but we'd have to deal with that, right? And our array would get twice as long, right? Okay, so yeah. All right, so because like I said, yeah, this corresponded to note C5, which was 523 hertz, basically. So just to make sure that we had everything set. So okay, good. Now, so that's it on the audio. Oh, one other thing to mention then, right, is sorry, the variable IM in the code. Basically, it just keeps track of, all right, as I'm processing voice 1, how long, how many notes, what duration of stuff have I put in? Okay. And let's say that I've put in 32 16th notes worth of stuff. I'm just making up a number. And then I'm done with voice 1. Okay, great. And now I start processing voice 2, and I end up with 33 16th note worths of stuff. Fine. Now I know that my song is of length 33 16th notes, and then that IM variable gets used in the playback to know how long do I continue? How do I know when to stop playing, basically? Um, Now, what would be much smarter is to pre-compute all of the frequency high low bytes and, excuse me, the control byte, um, and render it to a separate file that could then be read in by a separate program that's doing the playing. Okay, so that's a later assignment, is basically to write the program that does it. And to some extent, we could start with the code we've got, split it into 2 chunks, and then replace all of the things where we're writing to an array or reading from an array with disk writing or reading. Okay, and basically dump all these numbers to a seek file. Okay, but the only challenge then is going to be that the ordering is going to be different. What we would have to do is we'd have to have voice 1, voice 2, voice 3, rather than like we'd have to reorganize the data a little bit so that we're reading it in the correct order. That's not a huge problem to deal with, but it means that you're going to have to kind of rethink the ordering. Now, how do you know when you've hit the end of the file? Either for playback, well, on the playback side, well, if only there was a variable that told you if you've hit the end of the file, right? Wouldn't that be great? Yeah. Yeah, if you're reading a file, how do you know you've hit the end of it? If the status variable flips to what was it? One and yeah, a one in the whatever bit, the 6th bit. Okay. Okay, Gucci? Yeah? All right, so this isn't rocket science. What is, in fact, however, rocket science
We haven't even gotten music finished.
Yeah, that's okay. That means we can start talking about graphics. Okay, so graphics. The VIC2 and you. All right, so let me move this out of the way because I want to still have this open. Okay, so the VIC-2 chip is the video chip on this machine. And in the same way that the sound chip is a separate chip and has some of its own registers, so too does the VIC chip. The VIC chip, however, is much more complex because video is a lot harder than sound in some respect. Okay, now, the way this thing is sort of organized is the memory that the VIC-2 chip can see is not, it can't see all 64K worth of the memory. It can only see 16K of it at a time. And so we'll organize our memory into 4 banks, each of 16K. The lower 16K, next, and that gets us all 64K. Okay. The default for the VIC-2 is to read the first 16K of memory, so the bottom bank. And we'll talk about that, some of that stuff later. Okay. The control register at address DD00 hex is where you would set the bits to select which bank it has access to. Okay. Yeah. Now, that said, you do have to be kind of careful with that lowest bank because page 0 of memory and page 1 of memory are very special and not to be touched unless you are doing the appropriate thing because they have special purposes. So you do have to be careful. You don't really get all 16K worth of memory in that bottom bank. Okay. So the screen memory, there's sort of a couple ways to think about it and a couple of different modes that you can think about it. And right now on the screen, what you're seeing is an array of 1,000 locations, 25 rows by 40 columns. Okay. You also see a background color, which is the dark blue, and you see that light blue border that's around the outside. That's a separate thing. And those colors can be controlled for the entire background or the entire border separately, but it can basically only be one color, asterisk, footnote, that we'll deal with later. Okay, one color at a time, I should say. The background can be one color, the border can be another color, and there are 16 to choose from. Okay, which is kind of limiting, but hey, this is the early 80s. This is amazing.
How? Okay, so subroutines of just keeping things going on in the background. I want to run a program to change graphics on the computer, yet still give input. We're gonna have to use interrupts, right?
Oh, yes, which we'll get to.
This is just an OS class of this, guys.
Kind of. Except there is no OS. We're having to write our own. Right? Yes, we'll have to deal with interrupts in order to keep all this stuff straight. But we'll deal with interrupts when we get into the machine code because that's where it will actually be able to handle all that business. Okay, so the way this works is the default place where all of the character information is stored is starting at address 1024, which is 0400 hex, through 2023. So that's 1,000 locations. Okay. And the way that this works is if I write something to address 1024 with the poke command, depending on what I poke there, I will change what character appears in that position. Okay, so let me actually do that. Um, well, okay, so let me do this real quick. I want to poke memory address 1024 with a 0. And look what happened. Rippy, you weren't watching. What happened?
No, nothing.
Nothing. Let's do it again.
It was 7. One green. Oh, you're just. Can we change the color background?
We will.
Can we get bright magenta?
Yes, later. Right now I'm dealing with the text. Okay, so what I'm doing here is I'm poking the addresses 1024 through 2023. Silence, Rippy. Silence. Okay, I key. Um, contain 250, well, 256 values are possible in each byte, right? And it just so happens that there are 256 characters that we can put there. They come in two copies of 128. Okay. The lower 128 are basically regular text things, and the upper 128 are um, basically in reverse color. Okay. So, for example, let me do this again with the ampersand, which was number 0. Okay. So if I poke this address with 0, then it puts an ampersand there. If I poke it with 128, it's a reversed ampersand. So the background and the foreground switch. Okay. So you basically have two copies of each symbol, one regular and one reversing. Okay. Gucci? Now, this is only saying what character is displayed there. It is not saying what color that character is displayed in. That's handled separately, okay, which we'll get to in a second. All right, is that okay? All right, now, the screen memory, this 1,000 units of these 1,000 bytes can be moved in memory to a different location, okay? Its default values are between 0400 and 07E7, but it can be moved by modifying the upper 4 bits of this other register to basically say where to put it in memory, okay? And sometimes you have to do that. We'll work with the defaults for now, okay? Okay, good. Now, the question then is, where is the ampersand symbol itself stored? Because what I poked 128 or 0, I was just saying put character number 0 here, or put character number 128 here. But where is character 0? Where is character 128? How does the thing know what to put there? It just knows which symbol, or sorry, which code, but how does it actually know what the ampersand is supposed to look like? That has to be stored someplace, right? Yeah, and it is. It's stored in character memory. Okay. So the actual characters themselves are stored in ROM. Okay. And so on the board, the motherboard for this machine, there are multiple ROM chips. There's the basic ROM that has all the basic routines. There's the kernel ROM that has all the, basically the primitive operating system. And there's the character generator ROM that is smaller and basically has the preloaded values with how every character should look. Okay. And those things can be located in one of two different places, which is handy to be able to get to them from two different places. The default is an address is 1000 hex through 17FF hex. If you are in accessing in bank 0 mode, which is say the VIC is accessing that bottom 16K worth of memory, and it's 32K up from that. If you're in bank 2, you can also move it to 1800 to 1FFFF. And uh, the the way maybe to think about this is that's not where they're actually located. That's just where the VIC goes to see them. Okay. And so this is a little bit confusing, but the memory mapper, right, basically, where they are versus where the VIC thinks they are not the same thing. Okay. Now, if you are using banks 1 or 3 for screen memory, then you do not have access to the built-in character ROM. It's hidden. Okay. Which means what happens if you want to have pre-done characters from the character ROM? What you have to do is copy them into memory first, into your segment of memory, and then switch bank modes. Right. Okay, but we'll deal with that later. So, page 105 in the manual, of course, has a lot of the relevant information. And oops. Yeah, so for right now, we'll just work with stuff in default mode, everything as stock. Okay, now, what about color, right? So how do I change the color of stuff? Well, there are several registers and ranges of memory, okay? In addition to the screen memory, we also have color memory, okay? Screen memory says what character is there. Color memory says what color is it rendered as, okay? So for example, if I poke, what is it, 55296, and let me poke this with color 0, look what happened to the ampersand in the top left corner. Okay, what happened? Yeah, it changed color, right? And this one is in reverse, okay? So what is let me actually poke this one back to 0 so that it's a regular ampersand instead of a reversey one. Okay, what have I done? The background color is still blue, but what I've been able to do is change the color of the ampersand itself, okay? Now, what about if I want to change the background color? Oh, sorry, that was the border. I wanted the background. Okay, where'd the ampersand go? It's black on black, okay? And so if I want to change it to a different color, right? So that's color number 1 and color number 2 and so on. And there's 16 of these things that you can pick from, up to some of which are a couple different shades of gray.
So again, what you had to do to get this specific ampersand
Mhm.
was you copied some.
No, I didn't copy anything. All I did was I poked a particular memory address that corresponded with the top left, so the first position on the screen. I poked it with a number, the number 0, okay, which means I want to put character 0 there. The VIC said, okay, what's character 0? It's over here in ROM. That's how I need to display the thing that's located here. And then I went to a separate memory location to change what color it was. Isn't that fun? Yeah?
It gets upset. There's some things that gets really angry at it to try to do. So if you try to draw to the screen
Mm-hmm.
and you try to poke the color, it gets really angry.
Yeah.
Why?
Just you have to be careful, right? So, okay. So what this means is you can change each character's color, okay? But the background is affixed for all of them. Okay, the one exception obviously is the reversed colors, where it swaps background and foreground. Okay, but basically they're the same thing. Okay, does that make sense? Yeah? Okay, so this program that I wrote here, right, what is this going to do? Well, let's just do it. All right, so let me actually reset everything. Okay. All right, so 10 for I equals 0 to 15, 20, poke 55296 with I, 30 for K equals 1 to 200. Next, I'm basically just putting in a delay loop to slow it down. Yes. Okay, it's changing the color, but what's the issue there? Oh, yeah, I didn't. Good point. Oh, damn it. So I forgot that. But why did it not appear that anything was happening? Yeah, because which address was I poking here? The top left, okay, which right now doesn't have anything in it. Okay.
So you can't preset it to a color to do it.
Well, so let me put a character there. Okay. So I put a character there, and I cycled through all 16 colors, and I used the k equals 1 to 200 basically just to slow it down so that we could actually see them all changing. Okay? Is that cool? Oh, and I think Vice just crashed. Yep, it just crashed. Okay, so anyway, we get the idea, right? I can manipulate the color of any particular one of these 1,000 cells. So I'm essentially manipulating the color of the character. The background is fixed for all of them, and the border color is also a fixed quantity. Okay, and the background and the border colors, you modify those two registers to change them. Yes. Yes, I think. I don't remember what the command is called though. Just look at the wiki. There's a way to do it though. Um, even if you have to do division and look at the remainder. I mean, you could always just write your own little subroutine, right? Or function actually, because then it can return a value. Okay, so yeah, you can modify the color locations in addition to the what is located there, right? So each color also gets um, the so how many bits is each color, or how many bits are stored for each color? Oops, 16 bits, or actually it's 16 colors, so that's 4 bits, right? Okay, so let me put an ampersand back here. And let me also put an ampersand in that location. That's not what I meant to do. I meant to go 1 byte over. Okay, and now let me do this. So let me do let me poke 5, what was the memory address? 55296. Let me poke that with a 0. That'll make this one black. What happens if I go 16 or 32? No, it's fine. Yeah, basically, because all it's looking at is the lower 4 bits. Okay. And so if I do 16 or 32, the lower 4 bits are still the same. And if I do 255, that's the same as doing 15. Okay. This means that the color RAM is a little bit inefficient in the sense that we're wasting half of every byte. But it's okay. Yeah. Okay. So that's how we handle text and color. Okay. Now, let's do this fun example. Oops. Oops. Okay. Got the program? So what's it doing? We're in nested for loop hell. It's cycling through all 256 symbols in the first position in all 16 colors, and then when it finally runs through all the characters, which it just finished halfway, what's it going to do?
It's gonna crash your computer.
Nope. Well, it might. The program might crash. It's not going to cycle through again. It's going to, nope, move on to the next character, right? Because I'm doing this for every row. Okay. Now, if I want to have some real fun here, then I'll hit this magic button for warp mode. Warp mode. Yeah, basically I'm overclocking the processor, so it's going at 5x speed. No, that's I think the max you can do. Okay. Right. Now it looked like it was going slower because it wasn't rendering every single character to the screen. It was, but it was happening too fast for us to see it. Right. So this thing is going to cycle through every single character in every single entry along the top row and every single color for every single character. Okay. Because I didn't program it that way. Yeah. Okay. Um, Yeah, okay, but it's going through all of them and it's changing all the colors in the process, right? So that's cool, right? All right, so let me quit that. Yeah, that's all it's doing though, is I'm just kind of going through every entry of the first row. And I know I'm only in the first row because I only went up through 0 through 39. And how many entries are in the first row? Okay, and so then the next one would be entries 40 and on, right? And so on and so on. Okay. Um, right. So, okay. So that's cool. So carrying on. Okay. So how are the characters actually stored? They're stored, well, big shock, in binary, and they're stored in basically in uh, 8 by 8 arrays. Okay. And zeros indicate to be the background color and one indicate to be the foreground color, which is specified by color memory. Okay, so there's no actual color information attached to the character itself. It's just whether or not it's on or off. Asterisk will deal with that special case later. Okay. Okay. So the A character is located in memory's addresses D008 through D00F. That's 8 bytes worth of stuff. And A is the second character. So D000 through D007 is the ampersand. Okay, fine, right? All right, so I highlighted the ones in red here so that you could actually see them. Well, what does this define? It defines the letter A, okay? And what happens if I change those values? I can change the way the letter A looks. Now, what's beautiful about this, well, basically, yeah, we'll get to sprites later, but um, what this means is that I can change the way that a character looks, but not in terms of how it acts. So if I change the way the letter A looks, but then I start typing basic code that has that weird looking character, it still treats it as if it's the letter A. It's just how it looks is different. Okay, which is kind of clever, but hey, what? Yeah,
So then when you like loaded a game over here, it just changed all the text.
you could, yeah.
Yeah.
Yeah. So you could, for example, it depended on what you were doing, right? So there are a lot of symbols that perhaps you don't need for your character map, right? You've got 256 characters to work with. Now, should you probably have text in a game? Okay, probably, right? But that only needs 26 or maybe 52 if you're counting both lower and uppercase. You probably want the digits, so there's another 10. But do you need all of those? Like, do you need the pi symbol, for example, in a game? Well, Rippy's nodding his head like, how could you not have the pi symbol in the game? But point being, do you necessarily need all 256, or maybe better put, all 128 of those symbols? No, you don't, right? So you really only have 128 to work with, because what's the difference between the lower 128 and the upper 128? It's just palette swap, right? Um, so yeah, so you could redefine these, in fact, and use them to make graphics. It's like ASCII graphics gone to its most evil and despicable conclusion, right? Okay, I want to see some pretty cool rafflecopters, by the way.
But like, I'm just thinking of like how easy slash monotonous it would be to like program in like take the time, overwrite the characters, load them from a disk, program them into the C64, then use those characters in a separate like file that is also on that disk. And I'm assuming that's how these games would work.
A lot of them, yeah. Well, not all, but a lot, yes. You would use basically ask or characters as a way of doing some graphics.
Is this where the sprite palettes come in? Because it just reloads the level with a new set of sprites, like or like with a
No,
new
the
level.
sprites are a separate thing. We'll talk about those later.
But would it like could you load in separate like I guess overwrites of all of these things? So it's like you're in a different level, completely
Different
different
tile
color.
map.
Yeah.
Yeah.
Tile.
So you could use this for background kind of stuff, right? So, for example, let's say that you had Mario, right? Then, right, when you play Mario, what's going on? You've got all the blocks and the bricks and stuff that you're walking along, but there's also like the enemies that are walking and you are walking, and those two things are handled differently. Okay. Now, granted, for Mario, we're talking about the Nintendo, but the Nintendo works in a lot of ways similarly to the Commodore, similarly to a lot of these old 8-bit machines from the 70s and 80s. Okay. That they're all sprite based, and we'll talk about sprites later. Okay. All right. So, in basic mode, which is what the C64 starts up in, the characters should just be like things that you would want to type. Like, what else would they be? But they don't have to be, right? We can make them look funky. Okay, that is hex. I don't remember. Just multiply it out, right? Right. Okay. So you'll notice that I'm starting to use a lot of hex, and it's because what's sort of going to come and hit you guys upside the head in a week or two, where now everything's in hex instead of in decimal. Yeah, I do too. It'd be really nice if Basic could do hex, and the convention for um, uh, Commodore programming is that whenever something is written in hex, you put a dollar sign in front of it. Okay, um, just to indicate it's in hex. I didn't make that up, but that's the convention. Okay, now in our examples here, most of the time we're referring to memory addresses, and that's why there's 4 hex characters instead of just 2, because memory addresses on this machine are 16-bit, not 8-bit. The contents are 8-bit. Okay, what's wrong?
So you said that's located in D008, which is
Through D00F.
okay.
D008 is the top row.
Yeah. So
So where's the ampersand?
yeah, so if you have so if you try to poke, which is 4096 plus 8, and you try to poke that with any other number, it doesn't overwrite A.
No, no, no. D would be uh it's not 4096. It's gonna
16 to the first, 16 squared, 16 cubed, that's nothing.
yeah. So well, 1, 2, 3. It's 16 to the fourth times D,
Yeah.
and D represents, or 16 cubed. Sorry,
Yeah, and then it's like times the D.
which is yeah, which is 14, right? So we'd have 14 times 16 cubed is 57344. Okay, a plus 8, which would be 57352, right? So if I poke 57352 with a 0, say, do any of the A's change? No, because those addresses are the ROM, not the RAM. So I can't poke a ROM address. It's ROM, right? It's read only. Okay, so how do we redefine characters then? Well,
You have no refund, yeah.
yeah, you just have to bug me to do it because sometimes I forget.
I used to upload these slides.
Um, and if only the professor also live streamed everything. Okay, so now before I actually execute this, let's think about what the command is doing because this peek with a poke uh, construct is something that will in basic have to use a lot. So poke, I need to poke a memory address with a value. Well, what value am I poking? I'm poking whatever's currently in that memory address and it against 240 and I'm adding 12 to it. Okay. So peaking it and then using that as a formula for what to poke is how you can modify, like leave some bits the way they were and only modify some others. Okay. But if I just peeked this, I could see what's currently in that memory address. Okay. In fact, let's do that before I run this command.
Well,
Let's
so
hold on,
oh,
Rippy.
here's
Slow down. Peek. I need a print. Ah, print peek of 53272. Okay. Right now it's 21. Okay. All right. Now what I'm going to do is I'm going to poke 53272 with peek of 53272 and it against 240, adding 12. What happened? Yeah. Okay. So what happened? What I did was I told the VIC to start reading the characters from a different location in memory, the character data. But so I just told it basically to go to address 3000 hex instead of D1000 hex. Okay. And it said, okay, cool, that's cool. I'll go to memory and I'll start pulling characters from there. But what's in memory at location 3000 and on right now? Garbage, basically. So I need to put my own stuff there, right? Because right now it's garbage.
so you're saying, oh wow, that's added more stuff.
No, it's just that those little blips there were just whatever happened to be in memory.
Oh, so what you're saying is we need to take the palette, copy it into starting at 3000,
And then
and
change them. Well, okay, we only need to copy them if we want to use the the stuff that already is in ROM. If we want to make our own things, we don't need to copy anything. We just need to put what we want in those memory addresses. Okay, so let me reset this. Okay, which by the way is escape plus the page up key on your machines. And if you don't have a page up key because you're on a laptop or on a Mac anyway, it's function and then the up arrow gets you page up. And so the escape key is the run stop button on the Commodore, and the page up button is mapped to the restore button. And if you do those two together, it basically does kind of a not complete reset, but resets a lot of things. Okay. All right. So let's take, for example, what's on page 110. So let me load that program. Oops. Okay, so what this is going to do is switch everything to uppercase. Okay, we can ignore that. Reserve memory for some characters. Okay, fine, we can ignore that. Turn off key scan interrupt timer. That's important. Switch in the characters, and then it's going to basically copy all of our characters from where they were to where we want them to be. Okay. All right, and then restore the key scan interrupt timers. That is a technical thing that we'll deal with later. Okay, so if I run this, doesn't look like anything happened, did it? Except, what about if I poke? Now, where did we copy these things to? 3000 hex, which is what? Base 10? 53. Oh, hold on. Let me just not be an idiot. 12288. Okay. So let me take 12288 plus 8. So 12296. Oops, that's not what I wanted. Okay, hang on. Let me make sure I'm not forgetting something. Um, oh, right. I need to redo the previous command, which was this. Okay, so what just happened was the program that I ran copied all of the contents from the kernel, or not the kernel, the character ROM to starting addresses at C1000 hex, or not C1000, 3000 hex. Okay, and then I poked the location 3008, which is the top row of the A. I poked it with 0, which nuked everything. And so now look at my A. Yeah, okay, I made it look different. Okay. Now, the other thing that looks a little funky is what else? The cursor is sort of only half height. Okay. Whatever. Right? Huh? Um, yeah, because I think the cursor is stored. I forget. The cursor is sort of special for technical reasons. Okay, but you notice, did I change any of the characters on the screen? Did I change the fact that there was an A located at any particular point on the screen? No. All I changed was how A got displayed. Right? I could.
No, it did change model.
Oh, sorry. It changed how they looked. It didn't change the fact that those characters were in particular locations on the screen. So what I'm trying to remind you guys of, right, is that what so in the byte that stores what number or what characters is there, it's just storing the number one. How does character number one, which is the letter A, look? It's going into memory. We told it to go in memory starting with address 3000, or sorry, yeah, 3000 hex rather than out to the character generator. Yeah.
So those A's only changed because the whole thing shifted up. Because if it hadn't shifted up with the ready, those wouldn't have been refreshed, right?
No, they would have been.
They would have been.
Mm-hmm. Yeah, because see, I can poke, for example, what was it, 12296. Um, right? Yeah. Okay, so see now all the A's have a solid bar at the top. Okay. Now, in terms of defining your own characters, one thing the manual suggests is let me go back on the PowerPoint here to there. You see how anytime I have a vertical stroke, it's at least 2 pixels or bits wide. They recommend doing that because otherwise on CRTs, sometimes you wouldn't see that. Okay, so make it too wide in general is a good move. Okay. Okay, so yeah, so we can redefine our characters all the live long day. And what's so fun about this is, for example, if I say something like a dollar sign equals hello, and I print a dollar sign, BASIC still thinks that it's a dollar sign, even though the A looks funky, right? So how the character looks and how it's being treated by BASIC are two different things.
This could be so terrible so quickly. We just swapped all letters completely randomly.
Yes.
And it's still the same thing.
Yes, you could be really diabolical with this. So, for example, if I copied the way the B looked into where the A looks, then the A's would look like B's but function as A's, right? Which would be diabolically evil, but we could do it. Yeah. Okay. So, character memory. Great. Um, okay. So, let's look at page 111, which basically gives us some data sequences, because how many bytes does it take to store each character in terms of how it looks? 8. They're 8 by 8. Okay. And so if I wanted to modify each of those 8 bytes, I could do that with some data statements. And they do it. They redefine T to be a smiley face. Okay. Just as an example. Okay. So now let me go back to the here. Okay. So that's what's actually located there. What would my data statements for this be? Well, what is the top row in binary? It's 3 zeros, 2 ones, 3 zeros. What is that as a base 10 number? Well, I got what? 1, 2, 4, 8, and 16. So this would be 24. Okay, so if I wanted to store this as a data line in my basic program, I'm going to convert it to base 10 as 24, right? And similarly, what would the next one be? I'd have a 4, an 8, a 16, and a 32. What does that all add up to? Whatever it adds up to, right?
Would it be worthwhile to make a program that interprets neural strike as that?
It could. I mean, sky's the limit, Rippy.
There was one question I have about reading programs from the disk.
Mm-hmm.
If you load in a basic program that basically takes it in a disk, and it's like, okay, load program 1, load program 2, load program 3, that's going to get erased the moment you load program 1. So how would you load subsequent programs? Would you have to like connect them via like the end of the program? So if you load program 1 at the end, it says load program 2 from the disk?
Sort of. So there is, with the load command, if you do load name comma 8, says to come from disk number 8 comma 1, adding the 1 at the end says, okay, program loader, put it in memory where the program says to put it in memory. Because then you could load, and now that's going to be more relevant with machine language, okay? Because the machine language stuff can be put in memory wherever you want. So yeah, you can basically only have one basic program in memory simultaneously, but you can have as much machine language stuff in memory as you can fit. Okay, we'll get to that. Okay, all right, different character sets. We talked about that. Now, this kind of sucks because we only can do a single color basically per character. So you can also do what's called multicolor mode. And essentially what you do here is you sacrifice horizontal resolution for more colors. Okay, so if I go back to the letter A, okay, what I do is instead of thinking of the top row as being 8 pixels, I'm going to think of it as only being 4, and they're double wide. So I can use one character for these 2 pixels, another character for these next 2, another character for these next 2, and another character for the last 2, right? So I have the horizontal resolution at the benefit of having 4 colors instead of only 2. Okay.
So that doesn't change the actual resolution of the object. It just makes it so now
It
it's
looks chunky, right?
okay, so now it's two of those.
Right. Okay. So, for example, on pages 117 and 118, it's got some examples. All right. So let me reset what we've got, and let me load page 117 from Diskate. All right. Here's the program. It's going to set some background colors to, so you basically get 3 colors along with the background, and then it's going to turn on multicolor mode. It's going to set the value C to print to go to color memory, and then it's going to print a bunch of A's. Okay, just for our edification, and that's what multicolor text mode looks like. Now, in terms of using it for text, it's kind of unreadable, right? But if I were using this for something um, like bricks in a Mario game or something, I could build a level out of this sort of thing, right? And yeah, not going to use this for text. Like I said, it's essentially unreadable at this resolution, but I could do it, right? And so, yeah, like I said, what I've done is I've sacrificed um, horizontal resolution for doubling of the number of colors.
Well, then how did you get like better resolution text in addition to?
You didn't. I mean, it's 1982, Ribby,
Yeah,
right?
I mean you could. I mean, 4x4. I mean, you can still make decent text with that. I mean,
Oh,
as
okay.
these are defined now, terrible. But like, if you redefined all the characters to then take into account that 4x4, you could make readable.
But it's not 4x4; it's 4x8 because you're only having the horizontal resolution. The vertical resolution is unchanged.
Oh, it's still fine, right?
Kind of, because now it's sort of like your pixels are like rectangles instead of squares, so it kind of looks chunky, double wide. Yeah. I mean, yeah, you could. Now, that said, you could make sort of meta characters that are made up of multiple characters, but then how much information you can put on the screen is reduced. Okay, now that said, let me add one other thing. Um, the Commodore 128, which was a subsequent machine, I think in 1985 is when it was released. If you had a high res monitor, it could do 80 column mode. Whoa, right? But the 64, sorry, 40 column mode's all you got. So, yeah, pixel doubling, retina displays, 1080p.
How do you take like? So how does this take input? How are you like? How would you read an input if you want to change things on the fly?
Oh, you could read from the keyboard.
So, in terms of like how you do that, could we use reading from the keyboard to change what notes are being outputted so we can hear what we want? Specifically, so we can use arrow keys to go up steps or down steps.
Yeah, yeah, totally. Right, so you guys know the get function that we use?
Yeah.
If you don't put a hashtag and a number, then it defaults to reading from the keyboard, the keyboard buffer instead of a file. Yeah. So, of course, you can use the keyboard.
I mean, yeah,
Right?
but I didn't know how. I didn't know how it does them.
Yeah. Okay. So, all right. So there's those 2 examples there, which are kind of fun. Okay. Um, and then I guess where we'll pick up next time is with bitmap mode. Okay. And then we'll keep talking more about bitmap mode and multicolor bitmap mode and sprites and so on. Okay. All right. So I posted some new assignments. Let's just chat through those real quick. All right. So assignment 6, I think, is The music program, do it not stupidly, where you pre-compute it, like split the program into two chunks and use in file input and output. And then assignment 7 is write a program that can read a seq file and print its contents to the screen without using the print command. Hmm? Yes, by reading in each byte and writing to the appropriate location in character memory. And okay, whatever, right? And you can, the very first thing you'll do is you'll clear the screen by printing character number 147. That's the only print command you're allowed to use in your program. Okay, all that does is just clears the screen so that you have a fresh screen to start with. You can also assume that you have no more than 25 lines, and each line contains no more than 40 characters, so we don't have to deal with any weird line wrapping business. But that's okay. And then number 8, I think you guys will find fun. Make something cool that involves redefining characters and doing stuff. Okay. So actually, I did come up with another idea. Um, right. So you guys watched the Super Bowl? Yeah, the Coinbase commercial where it had the bouncing QR code, right? And of course, everybody scans it with their phone and it crashes the Coinbase web server because big shock, right? Yeah, well, you could make a QR code by combining a bunch of characters together to get the right shape, right? And maybe you'll have to redefine those characters. And maybe, so come up with something cool that involves redefining characters and printing and stuff and changing backgrounds and border colors and whatevers. Just please don't make me have a seizure, okay? Unfortunately, I'm not epileptic, but do something cool that doesn't, like, isn't Hypnotoad. Actually, Hypnotoad would be pretty cool, okay? Yes. So I'm giving you guys carte blanche with this one to do something cool, okay? So do something cool, damn it. All right. So we'll talk about bitmap mode and stuff later. All right. See you guys.